Hello there. So for this exercise, we need to consider the set of planes. Okay, so any generic plane could be a vector space, but it should satisfy a condition, and the condition is that this plane should pass through the origin. Okay, so here we got a generic definition of a plane in terms of set of points. So a plane that with a characteristic number b that corresponds to taking that b is related with the distance, is not this distance directly, but is related with the distance between the plane and the origin. That means that v corresponds to a translation. So if b is equals to 0, then we are in the case that we need to show b0 corresponds to the set of points x, y, z on the space that satisfy this equation x, y, z equals to 0. Okay, those are plotted here. So this is just a geometric representation of what this problem means. So any b of b with b different from 0 corresponds to a plane at some point that never touched the origin. Okay, and when v is equals to 0, then that means that the plane will intersect the origin always. And for this we need to consider an ambient space. This ambient space will be R3. So these vectors are subsets of R3. So these subsets can be vector spaces. It satisfies the condition that they cut they pass through the origin. Okay, so let me explain a little bit what's the definition of a plane in this notation, in case that you are not familiarized with this. This represents the normal of the vector, and this, as I mentioned, is related with displacement. So with respect to the origin, so you can see this in this way. So a plane can be characterized just by the normal, because it gives you the direction of the face, and it could be even negative. It doesn't matter. If normal is negative, you will define the same plane. So the set of points that the vector that will be represented by points, these vectors, that product with this normal, should be equals to b, that is related with the displacement with respect to the origin. Okay, so the points that satisfy this equation here will define a plane. If b is equals to 0, then this plane pass through or contain the origin. That is this case here. So in this case, this plane will be always contain the origin 0, 0, 0. Okay, and the set of points that pass through that point. So it could be this plane and so far. Okay, so that's just a geometric meaning. Algebra is always connected with geometry, so it's important to have that in mind. So you can think of this n is a vector, is a normal of this plane, as I mentioned you. So you can represent it as n1, n2, n3, and each of these vectors, each of these planes have a characteristic or fixed normal and constant v that is related with the displacement. So we need to show that these planes that doesn't pass through the origin cannot be a vector space. Actually, what we need to prove, the whole statement, is that b of b is a vector space if and only if b is equals to 0. So the first thing that we need to show is that if b is different from 0, then b of b is not a vector space. and then we will show that V0 is a vector space. So this is the first thing and this is the second thing. Okay, so let's do this. Let's start with the first claim, that if B is different from 0, then B is not a vector space. So how to prove this? Let's assume that B of B with B different from 0 is a vector space. We're going to prove it by contradiction. So B of B is a vector space with B different from 0. That means X, Y, Z are 3, such that n times X, Y, and Z is equals to B. Okay, so this is the definition of this space V, and the meaning that this is a vector space is that it satisfies the 10 axioms of a vector space. But let's pick one in particular. Let's see what happened with the fourth axiom that say that the 0 vector on that this space B of B should contain or should have a 0 vector such that any vector u in V plus this 0 vector is equals to u. So B of B is a generic vector x, y, z that satisfies this equation. So let's say that u is an element of this space B of B. Then u plus the 0 vector should be equals to 0 to u. But this is only possible if the 0 vector is equals to the 0, 0, 0 triplet. That means that x, y, z plus 0, 0, 0 is equals to x, y, and z. So it satisfies this equation here. But is this vector an element of B? And that is a contradiction. What happens if 0 is an element of B of B? Then this implies that this n vectors times the 0 vector is equals to some non-zero constant. Okay? But n is just n1, n2, n3, and let's say that they could be any number, n2, n3, non all 0. Okay, so none all of it of them are zeros. This dot product here is equals to n1, n2, n3 dot product with 0, 0, 0. This equals to what? To 0. But this should be equals to B, and B is different from 0. So here we have a contradiction. Therefore, B different from 0 implies that V is not a vector space. Or and this is equivalent to say that V is a vector space if B is equals to 0. Okay, so that's proof 1 part of the double implication. Remember that we claim that V is a vector space if and only if B of B is equals to 0. So we have proved this direction. Now we need to prove this direction. So if B is equals to 0, then B of B is equal to x, y, z on the reals, on the space, such that n x, y, z is equals to 0. Okay? So, how to prove this? So, well, here, yes. So we need to prove that this space B, or B0, is a vector space. So the first thing that we need to show is that the sum operation is closed. So let's pick U equals to U1, U2, U3, and V equals to V1, V2, V3. They are elements of B0. That means that both of these vectors satisfy this condition. Then the sum of these two vectors also are part of B0, means the plane that passes through the origin. Remember that here n is any vector that is fixed, so it's fixed. It's every non-zero vector fixed. So U plus B will be just a linear combination, if you can see it. So U, basically what we have here is that any vector in V0 is an element of B0 if it is orthogonal with respect to n0. So any vector orthogonal to n is an element of B0. So we have that U is orthogonal to n, and also that V is orthogonal to n. Then a linear combination of, actually any linear combination, any alpha U plus beta U V will be orthogonal to n. And here U plus B is a linear combination with alpha equals to 1 and beta equals to 1. Therefore, U plus V is orthogonal to n and therefore is an element of B0. So the sum is closed. So the first axiom is satisfied. The second axiom is related with the commutativity property. But here we need to consider something, and is that U plus B is an element of B0. And also U and B are elements of B0, which is a subset of R3. So U and V are going to satisfy the same axioms as R3. That means this condition, they commute. It's just a matter of picking this. U3 plus V1, V2, V3. This equals to U1 plus V1, U2 plus V2, U3 plus V3. So these terms can commute. So we got V1 plus U1, V2 plus U2, and here V3 plus U3, and this equals to B plus U. Sorry, V plus U, as expected. And this is because they are they are vectors in R3, so they satisfy the axioms under the usual summation. The condition here that they lie on or not on this plane doesn't have too much. There is no this condition that they lies on this space, on these planes, doesn't affect how the sum of, operates them. So actually, all the axioms in general satisfy the same conditions as R3 because they are vectors in R3. So the third, for example, u plus b plus w is equals to u plus v plus w is just a sum of vectors in R3. So they satisfy these conditions because they are vectors in R3. The only thing that we should prove is that they are close under the summation, and we have proved that yet. So if you want to, it is not necessary to check them all. They are hold because they are vectors in R3. So the axioms from 1 to the 5th holds because they are vectors. Sorry for the bad writing here. They are vectors in R3 with the usual addition operation. Okay? Now, the 6th axiom, we cannot assure that it holds because what the 6th axiom say that considering any k on the reals, which is a scalar, then ku and u an element of B0, ku also is part of B0. So now we need to again use the fact. So ku, so u, let's go from the beginning. If u is part of B0, that implies that there's n times u is equals to 0. This is equivalent to say that n and u are orthogonal. Ku is just an scaling. That means that doesn't change the direction. It only makes the vector bigger or smaller. So ku is parallel to u. That implies that n is orthogonal to ku, and therefore this is equivalent to say that n times ku is equals to 0. And this implies that ku is an element of B0, so is closed under the multiplication. And from the 7 to 10, the axioms holds because u, v, and w are elements on the space with the usual scalar multiplication. It is not necessary that you make all check all the axioms because the condition that they lies on this plane doesn't affect anything. So as a conclusion from this is that V0 is, so actually the whole statement say that if b is equals to 0, which is equivalent say that V0, this implies that B0 is a vector space. So we have proved that the both sides. So as a conclusion is that B of B is a vector space if and only if B is equals to 0.